Okay, hey everybody. So problem 33 is about, well, it's about this picture. So let's look at this first. So in the movie Hidden Figures, the mathematician has to compute this path precisely. Otherwise, the astronauts would potentially fly off into outer space forever and freeze, or they could crash into the moon, and that would be bad. Or anyway, so what they do is somehow they launch a rocket, and that means they're doing lots of acceleration and fuel burning. And then they get here and they sort of stabilize, and then they don't actually burn any fuel. They just are in free fall orbit. And they could just keep going like that, around and around in a circle. But then at some moment, they have to decide, and this is where the math comes in. You have to compute when should you fire your rockets, accelerating you onto a different orbit. And this new orbit does not go around the Earth. It takes you away from the Earth, and it takes you off into blank outer space with nothing there. And then meanwhile, the moon is flying around, and we have to compute exactly when the moon will come and be right at the right time as we're orbiting, so that now the moon sucks us in and we can go into a lunar orbit. And then we go down to the moon, and then we come back up and launch and go back into lunar orbit. And then at some point we fire the rockets and I guess we're over here then, and get back to Earth. So basically, what is required to actually compute this? Well, we have to determine when to fire the rockets. And then the way we determine that is by looking at this trajectory and seeing that it'll match up with where the moon is coming from and where the Earth is going, etc. And so I'm going to stop talking now. That's the setup. And so this is a differential equation. So gravity is a force, apparently, and force is equal to mass times acceleration. And apparently for gravity, that force is equal to the mass times some constant called g, the mass of the second thing, over the distance squared. And then it has a direction. It's a vector, some vector here. So this is a number. Actually, this whole thing is a number. But anyway, we're going to cancel the mass of the original object. And now I'm going to actually just erase everything and say, look, we have the Earth, we have the moon, and somewhere we have our spaceship. Okay? And so let's look at the force on our spaceship. Well, the Earth is going to pull our spaceship towards it, and the moon is going to pull our spaceship towards it. This is our ship. Okay, and so the total force on the ship is going to be a sum of, the Earth's force plus the moon's force. Okay, and what will those forces be? And in fact, we're not going to work with force because we're just going to cancel the ship's mass, and we'll say that the acceleration will be equal to the acceleration due to Earth and plus the acceleration from moon. Maybe from is an easier word than due to, so from Earth. Okay, so what are these? So what's the acceleration from Earth? Well, it's going to be some amount in this direction. And what is this vector? Final minus initial. It's the vector x1 minus x3. Okay, that's final minus initial. And we might as well just make it a unit vector. So let's scale it down. Let's normalize. Now we have a unit vector exactly in the direction that is pointing in the direction of the acceleration that our spaceship will feel from the Earth. Okay? And so then what is this number? How big of an acceleration are we going to get from the Earth? Well, it'll be I don't know why I'm switching colors. Anyway, it'll be g times, well, the Earth mass. The more mass of the Earth, the bigger the acceleration, divided by, and here's what science says, the square of the distance. So this length, the length of this vector here is the distance between our ship and Earth. Okay, and gravity varies inversely proportional to the square. That's what people say. But anyway, this is just a number right here. This is a vector. This is a number. And so we have basically a number, or I guess we call it a scalar. And then we have a unit vector, which is a vector. So now we have the Earth and the acceleration from the moon. Well, if I call the moon x2, then it'll be what? Final minus initial, x2 minus x3. And let's make it a unit vector, because then we know that we're supposed to use the distance squared, x2 minus x3 squared. So notice this is a different distance squared, because we're talking about the moon versus the Earth. And then there's this gravitational constant. This is some number that basically allows us to relate the actual physical world gravity with our choice of units, like meters and seconds. And so basically there's just some somewhat meaningless number just involving our choice of units that I'm not going to worry about too much. And then the mass here should be the mass of the moon. And since I called the moon x2, I'll say m2. So this is again a scalar and a vector. And what do you know it? We have a linear combination of vectors. That is the acceleration on the ship in total. Okay? Now, the problem is, at every moment, the moon is also being pulled towards the Earth, and actually the ship is even pulling the moon towards it. And then the Earth is actually being pulled towards the ship, a very, very small amount, and the Earth is also being pulled towards the moon, a very small amount. And in fact, somewhere else is the planet Saturn, which is also pulling everything towards it, and somewhere else is the sun, and that is pulling everything else towards it. And so you can imagine that this gets quite complicated. Okay, and so to simplify, we will consider the three-body problem: Earth, moon, ship. Now, finally, let's answer the question. What are the coordinates on this space? So this will be, I deleted part A. All I want you to do is these two parts. I want you to tell me what are the coordinates on this space, a higher dimensional space, which we will need for our vector field. And then what are the formulas for the vector field? And so first, let's talk about the coordinates. So we will need phase space R18 with coordinates coming from positions and also the velocities. We will need also the velocities of the Earth, the moon, and the ship. Okay. And so in formulas, what I will need to invent some names. So invent names. So our copy of R18 will be all the points like this: x1, 1, x1, 2, x1, 3. Those will be the position of the Earth. So the Earth will sort of be x1, the moon will be x2, and the ship will be x3. Okay. So here is the vector x1, and I've given it 1, 2, 3 coordinates. Okay, and we also need the velocity of the Earth. So v1, and now it needs 3 coordinates, so v1, 2, v1, 3. Now it has 3 coordinates. We have a velocity vector of the Earth. Somewhere is the Earth located at position x1 with velocity v1. Okay. And so this is the Earth, and this is the position, and this is the velocity. Okay. And now we need the moon, so that's x2. So we could do x21, x22, x23. That's the position of the moon. Then we also need the velocity, v2, v21, v22, v23. Because somewhere is the moon, and there's a vector, a three-dimensional vector pointing in where the moon is moving. We're not done. That's only R12. We need more coordinates. Oh my goodness, I need to give myself more room. Okay, we still need our spaceship. The position will be x3, and it'll have x31, x32, x33. Velocity will be v for velocity, 31, v32, v33. Okay. So that is our space. Earth, moon, ship. Okay. Now, that's part B, I guess. And I deleted part A. But for part B, I say we need a phase space R18 with the positions and velocities. And why don't I give a little picture? I'll put a picture. So somewhere in three-dimensional space, we have the Earth at x1. We have the moon at x2, and we have the spaceship at x3. However, the Earth has a certain velocity. The Earth is moving in some direction. The moon is moving in some other direction, and our spaceship is moving in yet another direction. And so those purple velocity vectors need also to have 3 numbers each, giving us 9 numbers right there for just the velocity vectors. But then the positions are also vectors. We can think of x1 is like that vector, x3 is that vector, x2 is that vector. We need to know where they are. So that's why we have 3 of these. This is the simplest, because otherwise you can start simplifying everything. Like you could just put your coordinate system. I could just put it at the Earth and have the Earth be at position 0, 0, 0 always. That removes 3 coordinates, so we could be down to R15. But it starts getting complicated the more things you do like that, like if we move it over there versus here. And so why don't we just treat all 3 of them sort of equally, even though this will be, in my opinion, simpler. Okay, so now we just need part C. So what are the coordinates on this space? We described them. Positions and velocities of the Earth, moon, ship. What are the formulas for the vector field? So part C. What are the formulas for the vector field? Recall that every ordinary differential equation is equal to a vector field on some phase space. In our example, phase space is R18. Okay? And then, solutions of the ODE will become curves in phase space whose velocities match the vector field. Whose velocities match the vector field. And this is just a rephrasing of an ordinary differential equation. So now, what is the vector field, though? The vector field is the ODE. So I'm asking basically, what is the ODE? So what are the formulas for the vector field? So a vector field has to be a map from the phase space back to itself. Every point in the phase space will get a vector. So every point in the phase space will get an 18-dimensional vector. that point. All the points get a vector. And then we want to find curves that sort of match those vectors at every point. Okay, so what's the formulas? Well, we know what we already invented in variable names for this. So let's call it x1. And I'm just going to sort of go like this, because I could write out like x11, x12, x13, but I already did that above. So whoever's reading my answer knows what it is. And I'll call this v1. Again, I could write out v11, v12, v13, but I'm just going to lump it together as a vector. It'll be simpler that way. And then I have x2 has three components, and then v2 is another three-dimensional vector, and then x3 is a three-dimensional vector. And I'm just sort of stacking them together. v3 is the 3. And now I got my whole 18-dimensional space, which is just one vector with 18 numbers. Now, where does it go? What is the formula for this vector field? Well, I'll tell you that half of it is easy. The position will then be updated by, well, exactly what this is. So we just put that there. So this becomes, in other words, v1 goes there. And then v2 goes there. And v3 goes there. Okay, so we just take whatever those numbers are and put them there. Take whatever these numbers are and put them there. Whatever these three numbers are, that goes there. Okay, so we're halfway done. We just need to know what to put in these 9 component functions. What are those 9 component functions? Well, now we go back to our whole formula. This, remember, is going to be a three-dimensional vector. 1, 2, 3. It's the acceleration. But the acceleration is just the time derivative of velocity. And so how does the velocity get updated? The velocity updates by this formula. Okay. I guess if this is the ship, I think the ship was 3. Yeah. And so let's actually write this out then. What do I put here? Well, same thing. I'm not going to actually give 3 different component functions. I'm going to use vector notation to make it easier. It's going to be some part from, okay, so what is this? This is the Earth. This is the moon. This is the ship. Okay. So the Earth is going to be affected, its velocity is going to change by acceleration due to the moon and acceleration due to the ship. And so there'll be a moon part and a ship part. That's how the velocity of the Earth will be changing. It'll be accelerated. The velocity will change by those 2. So let's see, what will go here? The Earth, if the Earth is here, then it'll be pulled towards the ship a very small amount. It'll be pulled towards the moon a very small amount. So there's the ship. So you see this vector is x3 minus x1. This vector is x2 minus x1, final minus initial. So that's what I need. I need some amount of x2 minus x1 and some amount of x3 minus x1. And I will add them together. Okay. Now, to make it easier, let's just normalize these vectors. Because then we know how big it should be. It should be the gravitational constant times, okay, this was coming from x3, from the spaceship mass, so that's the 3rd mass, divided by the square of distance, x3 minus x1 squared. This is some number times a vector. This will be some number, and then that number also needs a square of the distance times a vector. And that's it. That's the formula. So this picture became this formula for the acceleration of the Earth due to the moon and due to the spaceship. Now, in practice, this will be basically 0. In fact, even this might be basically 0, but not entirely. So we can, because the spaceship is so small. So this number m3 is so small that this whole thing right here will be basically the 0 vector. It'll look like that because I'm multiplying it by a really small number. Anyway, let's leave it. Okay, so now we will look at the moon. How should the moon accelerate? Well, then how should velocity change? Velocity changes by acceleration, so how does it change? Well, the moon is over here. So the moon will be pulled towards the ship, a very small amount, and it'll be pulled towards the Earth, a large amount. And so now I look at these pink vectors and I say, oh, this is not too bad. First, I need from the Earth, that's x1 minus x2. And then I need from, so I'm going to add to it from the spaceship, x3 minus x2. I might as well make these unit vectors so we won't get the distances wrong. So I just normalized each of them. And now I just put this constant, the g, the Earth's mass, because this is the Earth pulling on the moon, and square of the distance. And then here we get g and the spaceship mass, which will be very small, and square the distance. Okay, and we have one last formula. It'll be very, very similar. Let's take it to be a purple color. We have the spaceship. In fact, this is the one we're most interested in. And if we know the spaceship's velocity, we'd like to know how will it change in the next moment, and that will change due to acceleration. Partly acceleration from the Earth pulling on the spaceship, and partly from the moon pulling on the spaceship. Final minus initial. So let's take the Earth pulling on the spaceship and the moon pulling on the spaceship. Let's normalize them. Now we have unit vectors, and we want to know how much here and how much here. Well, that depends on the gravitational constant and the mass of the moon. And then we divide by the square of the distance. The gravitational constant, the mass of the Earth, that'll be a large number. Divide by the square of the distance. And there we have it. We are done. I will collect these all into a large vector. And a vector full of component functions. So this is 18 component functions. Notice if I zoomed in here, like the first component function, or this first component function is so easy. It's just v11. Okay. The second component function is v12. The third component function is v13. Just literally whatever number was there, we put it there. Whatever number was here, we put it there. Whatever number was here, we put it there. So anyway, the rest are more complicated. You know, this one, and this one. But they're linear combinations of vectors, and we've gotten pretty good at that so far. Yeah, so that's it. So I guess the only thing you really require is that you need to know what are these coordinates on this phase space, R18. Well, they're positions and velocities. Invent some names for them. Maybe draw a little picture to show why there are 18 numbers. Well, because we have 3 purple vectors and 3 blue points. Each point requires 3 numbers. Each vector requires 3 numbers. So that's 18. Second part is this formula right here. And the nice picture of how we get that formula right here. I guess you could draw 3 different pictures. I drew my 3 pictures on top of each other. But anyway, it's pretty fun to do this. I guess over here when I was doing it first time, I said more formally like Let x1 be the Earth's position, and v1 its velocity. Let x2 be the moon's position, and v2 its velocity. But you do it your own way. I definitely showed where the coordinates are. To predict the future means to have a curve in R18, some curve in R18, that will predict the future positions and velocities of the Earth, moon, and ship, all of them. Well, we will never get this formula. We will never find a formula for this. It's impossible. But we do know where we start. We know where we start. And so, and we know this vector field. We know a very explicit vector field. And so how did you actually compute the path? How do you do that? Well, you look at that vector field and you realize that where you start at the first moment, and the vector field tells you where to move inside of R18. But you don't care that it's higher dimensional because you know how to add vectors. So you just move there. Or really, you probably just move like a very small amount in that direction. Then you calculate the new vector field at that point. And then you move a very small amount in that direction. And then you calculate the new vector field at that point, just from your formula. You have the formula for the vector field. So you plug in at your new spot, your new point here, and you get some new vector. And then you follow that for a very short step. And if you repeat this with very small steps, you will eventually trace out a curve called the solution curve, or also called the integral curve, because you're sort of solving a differential equation, and integrals are usually the solutions of differential equations, so they call it an integral curve, anyway, so it's a curve in R18, and so you can do it, provided you can write down this formula. If you are able to write down this formula in a computer, then you can get the computer to predict all the different intricacies of where the moon will be, where the spaceship will be, where the Earth will be, even though you cannot write down a formula for this curve. You can get the computer to approximate it for you by little steps. Anyway.